Did you know that over 80% of the universe is literally hidden from us? That's right. There's something we can't see, touch, or directly detect, but it controls galaxy formation, holds the cosmos together, and might even contain the secrets of unknown forces of nature. What is this invisible matter we call dark matter? In this video, we'll dive into the greatest mysteries of dark matter, where it came from, how it shapes the universe, and the wildest and most plausible theories about its true nature. And the best part? By the end, you'll understand why solving this mystery could change everything we know about reality. Don't miss out. The universe is full of secrets, and this is one of the biggest. What is dark matter? Dark matter is one of the greatest enigmas of the universe. It accounts for about 27% of everything that exists, far surpassing ordinary matter, which makes up only about 5% of the cosmos. However, unlike ordinary matter, made up of atoms that we can see, touch, and study, dark matter is completely invisible. It neither emits, absorbs, nor reflects any kind of electromagnetic radiation, such as light, X-rays, or radio waves. This means our telescopes and conventional instruments simply cannot detect it directly. What we know about dark matter comes primarily from its gravitational effects. Its presence is evident in how galaxies rotate. Without dark matter, the outer edges of galaxies should rotate more slowly than their cores, but that's not the case. Dark matter also plays a crucial role in the formation and maintenance of galaxies, acting as a gravitational glue that prevents them from disintegrating. Despite this evidence, its composition remains a mystery. Is it made of particles we have yet to identify? Or are we dealing with something entirely outside the scope of current physics theories? Answering this question could revolutionize our understanding of the universe. What is it made of? The composition of dark matter is one of the biggest puzzles in modern science. Although its existence is evident through its gravitational effects, we still don't know what it's made of. Unlike ordinary matter, which consists of protons, neutrons, and electrons, dark matter doesn't interact with light or any other form of electromagnetic radiation, making its direct identification extremely challenging. One of the most explored hypotheses is that dark matter is composed of WIMPs, weakly interacting massive particles. These hypothetical particles would have significant mass but interact very weakly with ordinary matter, except through gravity. However, despite decades of searches in highly sensitive experiments like LUX and xenon, these particles remain undetected. Another intriguing possibility is axions, extremely light particles that might interact with electromagnetic fields under special conditions. Axions are promising candidates because they could explain certain anomalies in theoretical physics, but detecting them has also proven difficult. Additionally, there are even more exotic theories, such as the idea that dark matter consists of primordial black holes formed in the early moments after the Big Bang. Another speculation is that it comprises unknown particles belonging to a dark world with its own forces and interactions. Despite countless hypotheses, the truth is that the composition of dark matter remains an open question. Solving this mystery won't just help us understand the universe, it might also expand the boundaries of physics as we know it. How can it be detected directly? Detecting dark matter directly is one of modern physics' greatest challenges. So far, our understanding of its existence comes from its gravitational effects, but identifying its particles requires extraordinarily sophisticated methods. Since dark matter doesn't interact with light or other forms of electromagnetic radiation, scientists must rely on experiments that detect possible indirect interactions between dark matter and ordinary matter. The most promising experiments are conducted in underground laboratories, shielded from cosmic radiation and other interference that could obscure subtle signals. One example is the LUX-ZEPLIN detector, which uses tanks filled with liquid xenon. The idea is that if a dark matter particle like a WIMP collides with a xenon nucleus, it would generate a tiny flash of light that could be captured by ultra-sensitive sensors. Another approach is searching for signals from dark matter particle annihilation. In regions where the density of dark matter might be high, such as the centers of galaxies, dark matter particles could annihilate each other, producing gamma rays detectable by specialized telescopes like the Fermi Gamma Ray Space Telescope. Additionally, efforts at the LHC Large Hadron Collider involve attempting to create dark matter particles during high-energy collisions. Dark matter wouldn't be detected directly, but its presence could be inferred from missing energy in the reactions. Despite decades of research, none of these methods has confirmed the direct existence of dark matter particles. However, each attempt brings us closer to solving this mystery, and advances in technology may be the key to finally finding answers. What is its origin? The origin of dark matter is one of cosmology's greatest mysteries. It's believed to have emerged in the early universe shortly after the Big Bang, but the details of how and when it formed remain shrouded in uncertainty. Unlike ordinary matter, which formed from the combination of elementary particles like protons and electrons, dark matter likely originated from exotic processes not fully explained by current particle physics theories. One hypothesis is that dark matter was created during the universe's initial moments when temperatures and densities were extremely high. In this environment, hypothetical particles like WIMPs or axions could have been produced in large quantities. Unlike ordinary matter, these particles wouldn't have strongly interacted with radiation or other particles, allowing them to remain invisible to light while still exerting gravitational influence. Another intriguing possibility is that dark matter is a remnant of cosmic phase transitions. During the universe's early expansion, changes in physical conditions may have generated dark matter particles unlike anything else we know. Additionally, some scientists propose that dark matter might be related to extra dimensions or unknown forces of nature. If these ideas are correct, dark matter could be a fundamental component in understanding not only our universe, but also a broader multiverse. The key to uncovering the origin of dark matter may lie in experiments that study the universe's earliest moments, such as observations of the cosmic microwave background or advanced computer simulations. Each new discovery brings us closer to answering one of the most fundamental questions: where did we come from, and how did the universe take its current shape? How does it affect galaxy formation? Dark matter plays a vital role in the formation and structure of galaxies, acting as a kind of gravitational glue that holds galaxies together. Without dark matter, galaxies as we know them likely wouldn't exist, as the gravity of ordinary matter wouldn't be enough to prevent stars, gas, and dust from dispersing into space. Shortly after the Big Bang, the universe was a nearly uniform mix of ordinary matter, radiation, and dark matter. Over time, small density fluctuations began to grow, driven by gravity. Dark matter, being insensitive to radiation, started clumping together more quickly than ordinary matter, forming invisible halos that served as gravitational cradles for the first galaxies. These dark matter halos influence the distribution of stars and gas in galaxies. The rotation of spiral galaxies, for example, is one of the main pieces of evidence for their presence. Observations show that stars on the outer edges of galaxies rotate much faster than expected if only visible matter were present. This suggests that a massive halo of dark matter surrounds each galaxy, providing the extra gravity needed to explain this behavior. Additionally, dark matter plays a key role in larger cosmic events, such as the formation of galaxy clusters. These clusters, which can contain thousands of galaxies, are held together primarily by the gravity of dark matter. Studying how dark matter shapes galaxies helps us understand the dynamics of the current universe and provides clues about the evolution of the cosmos since its beginnings. The complex interaction between ordinary and dark matter is still being investigated, but it's clear that without dark matter, the universe would be a completely different place. The relationship between dark matter and dark energy. Dark matter and dark energy are distinct concepts, but both are essential for understanding the universe. Together, they make up about 95% of the cosmos. While dark matter accounts for 27%, dark energy is responsible for approximately 68%. Dark matter acts as a gravitational glue, holding galaxies and clusters together, while dark energy is the mysterious force driving the accelerated expansion of the universe. The relationship between them remains a mystery. Some scientists speculate that they may be connected through mechanisms not yet understood by physics, possibly involving particles or forces beyond the standard model. Studying this connection could reveal new fundamental laws of nature and shed light on how the universe has evolved into its current form. Could there be interactions beyond gravity? Currently, dark matter is detected only through its gravitational effects. But a big question remains. Could it interact with ordinary matter or with itself through forces beyond gravity? This possibility is an active area of research with profound implications for physics. Some theories suggest that dark matter might interact through a new fundamental force yet to be discovered, called the dark force. This hypothetical force could explain unusual patterns observed in the distribution of galaxies and the behavior of dark matter halos. Additionally, experiments are searching for direct interactions between dark matter particles and ordinary matter, such as the recoil of atomic nuclei in detectors. If such interactions are confirmed, they could provide information about the composition and properties of dark matter and pave the way for new physical theories beyond the standard model. Exploring these potential interactions brings us closer to understanding dark matter's full role in the universe and revealing hidden dimensions of the cosmos. What if we're wrong about dark matter? While dark matter is widely accepted as an explanation for unexplained gravitational phenomena in the universe, some scientists question its existence. They argue that instead of postulating an invisible substance, perhaps we need to revise our understanding of gravity. One alternative theory is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on cosmic scales. According to this idea, the effects attributed to dark matter could be explained by a modification of gravitational laws. Another hypothesis involves the possibility that our current cosmological model is incomplete or incorrect. Perhaps there are unknown forces or particles simulating the effects attributed to dark matter. If these alternatives are proven, it would revolutionize our understanding of the universe. However, dark matter remains the most consistent explanation with the available data, such as galaxy formation and gravitational lensing. The scientific challenge lies in exploring both possibilities, keeping an open mind for fundamental revisions in the future. This constant search for answers reflects the essence of science: questioning, investigating, and learning more about the cosmos.